Hello and welcome to the MOOC on Applied Electromagnetics for Engineers. We were discussing the propagation of step-like transient voltages on a transmission line in the previous modules. In this module, we will consider even more practical case of a pulse propagation. This is a very common case. So, take an example of an FPGA or a microprocessor board and look at where the clock would be located, or you generate a clock. You would see that around the FPGA there would be lot of other secondary components that would be present, okay, or even inside an FPGA there would be one unit which would be the clock unit, and this clock would be supplying via buses, it would be supplying clock to several other sub modules or several other chips it would be generating. Or if you consider a backplane connection that is happening to the main card or the daughter card to the motherboard connections, there would be transmission lines which would be where one end would be a clock typically, or another digital or an information carrying or an information symbol, and that would be mostly in the form of a pulses, and these pulses would be propagating on the transmission line. Okay. Even address changes could be thought of as pulses propagating on the transmission line, with the pulse duration being slightly larger. So, it is very important for us to understand what is happening when a pulse or a pulse source is connected onto a transmission line. Okay. We can analyze how a pulse would propagate on the transmission line by the same methods that we have used for analyzing the step-like voltage transmission line. Remember, in the step-like transmission what we did, we took a step, we calculated the initial or the first voltage that would be generated because of the step source, propagated, had multiple reflections because of the mismatches that would exist at the load and the generator side, and at any point on the transmission line that if you want to know how the voltage would be changing, you would simply have to draw a particular line that would connect the space-time diagram. So, the Z slice would connect the time slice, okay, and then you would count whatever the voltage and then you would plot that voltage. Okay. You can perform the same operation, okay, if you imagine a pulse to be composed of step voltages. And how do we do that? Well, it is very easy. A typical pulse would be of this fashion, right. So, you would have a pulse of duration t units or t time seconds, and we will call this as the duration of the pulse. It would have some amplitude of V0, but you can imagine that this pulse is actually made out of two step voltages. One step voltage would be V0, and then there would be another step voltage which would be minus V0 in amplitude, that is exactly opposite to the amplitude here, which would begin to propagate at t seconds. Okay. So, the sum of the voltages, the sum of this first step and the second step would obviously give you a pulse whose duration would be of t seconds. So, I can adapt the same lattice diagram construction that I have done, except that I initially propagate this V0. I could construct another lattice diagram and consider the propagation of the minus V0 step starting at capital T seconds. However, we can in fact put both of them on the same lattice diagram. The suggestion would be to use different colored pens, okay, to distinguish the propagation of a plus V0 voltage and a minus V0 voltage. Okay. So, let us see by way of an example how this is performed. Okay. We consider a pulse source. So, I am using this one to denote the pulse source. Let us assume that the pulse is about 40 volt, okay, and a 1 microsecond wide pulse. I have purposefully chosen this one to show you a certain concept that would arise in the pulse propagation. In practical situations, this voltage would be around 0 to 3 volt, okay, as long as we are considering digital circuit boards, and the pulse widths are typically nanoseconds. Okay. This pulse voltage source is connected by a 150 ohm generator impedance and connected to a transmission line. Okay. I am no longer writing a t equal to 0 kind of a switch, because the pulse itself will begin at t equal to 0 and will be terminated at t equal to 1 microsecond. We consider a 50 ohm transmission line. We do not bother too much about what is the length of the transmission line, except that we want the pulse width here, which is 1 microsecond, to be less than the time delay. So, let us consider say 600 meter long transmission line with the velocity of 3 into 10 to the power 8 meter per second, we already know that the delay here would be about 2 microseconds. So, we consider the same parameters as in the last module, except that now the voltage source has become a pulse. We will consider a resistance or resistive termination with a resistance of 16.7 ohm. Obviously, this value of 16.7 ohm was picked for mathematical convenience. Why? Because it makes gamma L equal to plus half, okay, and gamma G would also be equal to half. You can calculate this and verify that this would indeed be the case. So, this is just to make the numbers look better. If you have a calculator or if you can write a program in order to automate the entire thing, you do not have to necessarily do all these convenient cases. Okay. How do I write the lattice diagram? Let me erase this equivalence of a step voltage and the pulse voltages so that I can make some space in order to draw the lattice diagram. So, I have the space time diagram or the lattice diagram in which the z axis is stretching from z equal to 0 to 600 meter. Now, I begin to propagate the first voltage, which is V1 plus, corresponding to a positive step. So, I am going to begin propagating the positive step of V1 plus voltage, the first voltage, which is given by 40 into 50 divided by 150 plus 50. Of course, this one is nothing but 50 divided by 200. So, that would be 5 by 4. So, 4 and 4, that would be about 10 volt, right. So, this would be the pulse amplitude that would begin to propagate. So, let us begin a 10 volt propagation which goes up to 2 microsecond. At this point it gets reflected, becomes only 5 volt because gamma L is equal to minus half. There will be further reflection of 5 volt from the generator side. So, this will reach the generator at 5 microsecond and there will be further reflected, and the reflected voltage amplitude will be half of 5, which is 2.5 volt. Then there will be further reflection which would be 1.25 volt, and this continues to happen like this, right. So, this would be happening at 6 microsecond. The change here will appear at 8 microsecond, then there will be a 10 microsecond and so on. Okay, this so far looks almost like what we have been doing in the earlier time, right. In the earlier modules, we had a step voltage of 40 volt applied to the transmission line circuit. So, this was our transmission line circuit and we have just looked at the propagation. But now remember, there will be a second step that we are going to apply, and this time the step that we are going to apply will be at 1 microsecond. So, as soon as I am done transmitting this 10 volt here, I need to next start transmitting a minus 10 volt. Okay, that would be the initial voltage. Okay, so this would be the initial forward voltage because of the minus 10 volt step that is appearing at 1 microsecond, right. And this would reach the 600 meter load section at 3 microsecond, get reflected, reach at 5 microsecond, further get reflected, reach here at 7 microsecond. What is the reflected voltage here? Minus 10 and half, so that would be minus 5 volt. Minus 5 volt getting reflected further by half will make it minus 2.5 volt, and minus 2.5 volt reflecting further will give you minus 1.25 volt and so on. So, from 7 this would reach at 9 microsecond, and from 9 this would reach at 11 microsecond. So, minus 1.25 volt and further reflection. So, you can see that I have kind of compressed both the blue lines as well as the red lines. The blue line corresponding to the step at t equal to 0, and the red line here corresponds to step at t equal to 1 microsecond. Okay. So, in fact, what I have done is to take this pulse whose height was 10 volt and transmit it out there. So, that is what I have actually done. So, I have taken this initial pulse and transmitted. So, there is actually a reflected pulse here, then there will be one more reflected pulse, another reflected pulse, another reflected pulse and so on. Okay. Now, let us plot what would be the voltage at the source side. What would be the voltage at the generator end? So, let us mark the time axis. So, what we now have is a 10 volt signal that is propagating. Okay. However, there will be a minus 10 volt step propagating at 1 microsecond. So, initially I begin propagating at 10 volt, but immediately at 1 microsecond after the propagation of the first voltage, I need to propagate minus 10, and 10 and minus 10 would make the total voltage go to 0, and therefore you will actually have a pulse of duration 1 microsecond. So if I mark all the time axis in terms of microsecond, there will be a 1 microsecond pulse of height 10 volt that would have propagated. Okay. So this is what has propagated, because the change to the blue line is happening at 4 microsecond. So by 4 microsecond, the sending end side pulse is completely extinguished. So the change that would happen now, let's mark out 2, 3, 4, 5, 6, 7 and 8 microsecond. So the change that would happen will happen at 4 microsecond. At 4 microsecond, what would be the voltage that would be propagated? It would be 5 plus 2.5. Okay, so it would be 5 plus 2.5. So this would actually be 10 volt, reflected is minus 5 volt, reflected is minus 2.5 volt, reflected back here is plus 1.25 volt, which is all right. And then this would again be reflected as half of 1.25 voltage. So how much is half of 1.25? That's about 0.075 voltage. Similarly, a minus 10 volt here would propagate, and then it would be reflected into plus 5 volt. Okay, a plus 5 volt would be reflected by and makes it plus 2.5 volt. A plus 2.5 volt further gets reflected by plus 2.5 and minus half, which is minus 1.25, and further in that fashion. So now what happens at 4 microsecond? What is the total voltage that you are receiving? You are receiving a minus 5 volt and you are sending out minus 2.5 volt. So the total voltage at this point would be minus 7.5 volt, and that would be negative voltage, right? So at 4 you begin to have a minus 7.5 volt propagating, but immediately at 5 microsecond, okay, you would receive a plus 5 and a plus 2.5, that is plus 7.5 volt you will receive, which means the voltage again goes back to a pulse like manner. So this would be minus 7.25 volt. The next change will happen at 8 microsecond, wherein you are receiving 1.25 and transmitting or sending half of 1.25, okay, and that would be about 1.875 volt. This time it would be positive and it would last from 8 to 9 microseconds. So this is 1.875 volt and so on. Okay, so this is how the voltage would look at the source side. So you will see a sequence of pulses being propagated. Okay, so if the transmission line length is much larger, if the propagation time is much larger than the pulse width that you have considered, there will be multiple reflections of the pulse, and it's actually a big problem for you, because if this pulse goes and then there will be the spurious reflections, your sender might not really work correctly, because it is now receiving a minus 7.25 volt, whereas it simply does not expect it. You want the 10 volt signal to simply go to the transmitter, whereas these spurious reflections that you are going to see are actually going to create problems for the entire link. So the fidelity of the link is completely compromised because of these spurious reflections. Okay. Let us consider the opposite scenario, that is, we will consider the case where the propagation time is much smaller compared to the pulse width itself. Okay. So for that, what we can do is, we will consider all the parameters to be the same, except that the pulse will be 5 microsecond wide. Okay. The propagation delay is 2 microsecond for this circuit, whereas the pulse itself is 5 microsecond. What it means is that there will be a positive step of 10 volt in the initial voltage that is launched, and there would be a minus 10 volt launched at 5 microsecond. So at 5 microsecond there will be a minus 10 volt launched. So what will happen to the lattice diagram? Let us rewrite a lattice diagram here. So this time this is the lattice diagram that I am drawing. Okay. So we have z equal to 0 and z equal to 600 meter. This is the z axis, this is the time axis. Let us begin the propagation. So first we will have a 10 volt signal propagating, or a 10 volt step propagating. This would reach at 2 microsecond to the load, where it would be reflected to become minus 5 volt. Why would it be minus 5 volt? Please remember, gamma L is minus half here and gamma G is equal to half. So the reflected voltage at 2 microsecond would reach the generator at 4 microsecond, where it would promptly be reflected further to minus 2.5 volt, which will reach the receiver or the load side at 6 microsecond, where it would again be reflected off with a value of plus 1.25 volt, and there would be one more propagation, because this would reach at 8 microsecond, this will reach at 10 microsecond with 0.075 volt. So this is how the first V0 has propagated. Now what about the second V0? Where should the second V0 step begin, or minus V0 step begin? It should begin at 5 microseconds. So if this is 4 and this is 6, so let's begin here at minus 5. The initial launch voltage is minus 10 volt, and that is what begins to propagate, and it would reach the receiver side at 7 microseconds. So it begins at 5 microseconds, reaches the receiver, where it would be reflected back by the receiver. So this is minus 10 volt. Okay, the reflected voltage will be 5 volt, because minus 10 into minus half, so that makes it 5 volt. Again there will be one more reflection. This 7 microsecond reflected step voltage will reach here at 9 microsecond, and this one will again change, or this will again reflect back. Okay, what would be the reflected voltage here? 5 and a half, that would be 2.5 volt, and there would be further reflection. This one would reach here at 11 microsecond, and it would be further reflected, and so on. You can see that the red curves are starting after at least the first forward voltage has actually come back reflected from the generator end. So if it would be very interesting for us to see what kind of the voltage distribution that would exist again at the source side. Okay, you can write down the voltage at different points on the transmission line, especially at the load side, as exercises. We mark the points here at 0 this time, because you have all the changes happening. So let us mark it as 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, maybe we can also mark this last point as 10. Okay, so we have 11. So this is my time axis. This all time axis is in microseconds. So time axis is in microseconds. Okay, look at what happens. Initially the voltage would be 10 volt, and that would continue to remain until 4 microsecond, right? So until 4 microsecond you have launched a 10 volt step which would continue to propagate, but at 4 microsecond your total voltage should decrease, because there is a minus 5 reflected and a minus 2.5. So the total voltage here will be 10 minus 5 is 5, 5 minus 2.5 is 2.5. So this has to drop down to 2.5 volt, and until what value this would remain? It would be the same case until you reach up to 8 microsecond. At 8 you would receive a plus 1.25, and you would send out a 0.075. So to already 2.5 volt you would receive a plus 1.25 plus 0.075. This would be 5, 2, 3, 1.325 plus 2.5 that you already have. The total voltage that you are going to get will be 3.825. So it would jump to 3.825, and it would continue to be the same case at 9 microsecond. There will be, so we completely forgot what happened at 5 microsecond. Okay, so this would continue at up to 2.5 microsecond, but at 5 you will actually have launched a minus 10 volt, right? So because you have launched a minus 10 volt, this total voltage would now be reduced. This should actually become minus 7.5 volt, because there is a jump of minus 10 volt. Okay, and at 8 microsecond you would receive a plus 1.25 and a plus 0.075. So this would be 1.325. So to minus 7.5 you need to add 1.325. Okay, so this becomes 1, and this would be minus 6.175 voltage. So it would just go up and become minus 6.25, but at 9 you would receive a 5 volt plus a 2.5, that is 7.5 volt you would receive. So 7.5 volt you would receive. So the total voltage would be 5, 2, 3, 1.325. So this change would have made at 9 the voltage value of 0.725 volt. So you can see that the voltage is actually getting distorted because of this multiple reflections. Okay, so in both cases, in one case you had pulses, multiple pulses between the transmission line propagating and coming back, and in this case you have the transcending end pulse that is completely distorted because of this transmission line effects. Okay, you did not expect this negative big large pulse, but unfortunately that is what you are going to get. Okay, before we close the discussion of pulse propagation and we go to the other module, I have an important kind of a setup that I would like to consider. Okay. Here let me assume I have some voltage, that is some Vg, which of course I am going to now not assume a pulse, I am assuming a step voltage, and it has some Rg, but this time we choose Rg equal to R0. Okay. And then connect this one to a transmission line circuit and monitor the voltage at the input terminals of the transmission line. So, I am monitoring the voltage at V equal to Z, V at Z equal to 0 as a function of time. Let the characteristic impedance of the transmission line be R0, which is completely known. However, the transmission line whose length is known to me, okay, I do not know what load is connected on the other side. So, RL, the connecting load or the terminating load, I have no idea. I am let me assume the step voltage of value Vg. Okay. So, clearly if I were to write down the lattice diagram, what I would observe is that an initial voltage of Vg by 2 will be launched at the input terminals of the transmission line. At the reflection, because of the reflection at the load side, the voltage that would be coming back will be gamma L times Vg by 2. Assuming gamma g to be real, it could be either positive or negative, but it would be real because of the resistive termination. The receiving side voltage will undergo a total change. The receiving side voltage will undergo a change of gamma L into Vg by 2. Will there be further reflections here? Unfortunately, there won't be any further reflection because we have made gamma g equal to 0. Gamma L is some real number. It could be minus 1 less than gamma L less than 1. But I do not have an idea of what the value exactly equal to. So, my goal would be to look at the voltage or monitor the voltage at the source end and try and figure out what would be the load that is connected. Can I do that? Yes, indeed I can do that. Let us first consider the general case, and then start looking at, let us first consider special cases and then develop an idea of how to do that. We look at the voltage, that would be launched from the generator side. The initial voltage step that would be launched will be Vg by 2. Why would it be Vg by 2? Because Rg is equal to R0, so the voltage divides itself into half. In some cases, people actually, instead of using Vg, they will use 2 Vg, so that the step voltage itself is Vg by 2, but it does not matter. I mean, you can call Vg by 2 equal to V0. Okay. Let us call this as Vg by 2 equal to V0. So, this is launched. And when will you see a change in this voltage? The change will happen at 2 TD, right. So, at 2 TD there should be a change happening. Suppose RL is equal to 0, that is short circuit. What would be the meaning of a short circuit? You launched a V0 voltage, however the receiving or the reflected voltage because of the load RL equal to 0 will carry a minus sign, right. So, whatever the voltage that you are receiving will be multiplied by minus 1 and reflected back, and when this reflected voltage reaches, it would be completely absorbed at the source side because gamma g is equal to 0. So, the voltage change that would happen will happen at 2 TD, where a minus V0 voltage is received. Already V0 was propagating, now a minus V0 is received. Therefore, the total voltage that you would see would drop down to 0. So, this is what the voltage that you would see. So, whenever you see such drop, you can immediately figure out what was the voltage jump that you saw, that was minus V0. You could immediately figure out that there was actually a short circuit which made completely the voltage at the generator side drop down to 0, that is at the input terminals of the transmission line the voltage completely drops down, jumps by minus V0. Now, suppose I tell you that the voltage did not jump down by minus V0, but rather jumped up by plus V0, that is the voltage here that you are seeing is 2 times V0, 2 times V0 is of course equal to Vg, right. So, what is the type of load that would have given you a jump here of a magnitude equal to V0? That load could only be a open circuit load, because for an open circuit load gamma L will be equal to plus 1, therefore you would see a jump. If RL happens to be anywhere between the short circuit to the open circuit, right, it can be anywhere between short and the open circuit, jump accordingly will be less than V0 or in the negative direction, or it would be on the positive direction. However, the magnitude would always be less than V0. Suppose I tell you that the jump has been at half V0, that is the jump of the voltage has been half V0 and it was actually on the positive side. Now what can you conclude? Clearly you can conclude that gamma L must be positive. Only a gamma L that is positive can give you a positive jump at 2 TD, right? From the initial launched voltage you can jump only for that. So clearly you can, by measuring the voltage jump, also figure out that gamma L is positive and is equal to half. This means this is equal to RL bar minus 1 by RL bar plus 1, where RL bar is the normalized load that I am considering. You can solve this and then find out what would be the corresponding load impedance, but you know that RL has to be greater than R0, otherwise you would not get this as a positive quantity. Suppose I tell you that the voltage, instead of jumping up, jump down by say minus 1 by 3 V0, then you know that gamma L is equal to minus 1 by 3. Again this would be equal to RL bar minus 1 by RL bar plus 1. Clearly in this case RL was less than R0. You can find out what is the exact value since you already know what is gamma L. So this is something that you can do, if you are measuring resistively terminated loads and you don't know what is that resistively terminated load that is connected to the transmission line circuit. In fact, manufacturers have come up with a nice product that can not only tell you what is RL but can also tell you what is ZL, that does not rely on the steady state behavior of the line. So there is no more slotted line type of a measurement, but this measurement is happening in the time domain, and this device which can tell you what is the value of the unknown load by making measurements in the time domain. And usually it won't be a step voltage, it would be a pulse voltage, because the processing becomes slightly easier for the pulse case compared to the step cases. And that instrument, which is available in the market and used by many PCB designers, is called a time domain reflectometer. It works more or less like a radar. However, the complete discussion of a time domain reflectometer, we will take it up in another application oriented module. Until then, thank you very much.